Hi guys, it's Talha back here again today, and you guys need to welcome me because I'm here after a whole, I think, week because I went to Lahore for a university tour, and I came back on Thursday, and yesterday I was a little tired, so I decided not to make a video. But today I am making a video just because I want to maintain the flow, and I think I'm also going to make a video tomorrow. If not, I'm surely inshallah going to make a video on the coming Monday. So today we are just recapping what we studied earlier. I've already made the videos on these topics, but just to recap, because I just rushed through these topics, but in this video I'm going to go into detail of what needed to be explained. So now what I'm going to explain is about a uniform continuous distribution. I've already made a video on this, but just to recap, I'm going to explain it again. So I have a uniform continuous distribution. Then I'll go on to the next topic, that is our left and right hand limits, or you can say that one-sided limits. I'll explain what they are. I've already made a video, but I'm going to explain in detail what they are, and one-sided limits. And then at the end of the video I'm just going to tell you guys about the assignments we needed to do, we were supposed to do for the statistics, for the stats, and for the programming subject. So if we have time, I hope we have time, we'll have time for all of these three categories I'm going to cover in this video. So let's start off with our uniform. Let's start off from our uniform continuous distribution. So as I explained earlier in my videos, that uniform continuous distribution is for the random variables which is of the nature continuous. So earlier I've explained that we have binomial distribution, we have Poisson distribution, and we have hypergeometric. So all of these distribution are for discrete random variables, but this one, uniform continuous distribution, is for continuous random variables, because in a continuous variables the probability of an exact number of or an exact thing to occur is actually zero, so you have to take intervals. So a random variable or a probability function of a p of x, when x assumed little x, is said to be a uniform distribution if this equals 1 divided by b minus a, where x, or where little x, is greater than your a and less than or equal to your b. So then this function is going to be called as uniform continuous distribution function, or this distribution is going to be called as uniform distribution, where you have a continuous variable. So let's solve some examples. So we have okay, let's first derive this formula. How did we get this formula first? So for example, we have a graph here. We have a graph, and let's say that our a, let's say this is our a and this is our b. So this is our a, this is our b. All the probability over here is equal to 0, means less than a is equal to 0, and the probability greater than b is also equal to 0. But from a to b we have a uniform probability. So all of this area our uniform probability, and this is our f of x. This is our f of x. So, as we know that in a continuous distribution, the area under graph is your total probability, and that has to be equal to 1, because the total probability is equal to 1. But here in uniform distribution, you have the total area under the rectangle, because the probability is uniform. So the probability of any point of any two areas, for example, we have this area, and for example, we take this part and this part, given that the length of these two line segments is the same, the probability of these two um, probability of these two areas will be the same, will also be the same, because it's a uniform distribution. And in a uniform distribution, we have the same probabilities of any two given line segments having the same length, and these two line segments will have the same area, because it's a rectangle. So that is why we say that in a uniform distribution we have the probability, we have the area of the rectangle, unlike the area under the graph in a normal continuous function or continuous distribution. So we have this area, we have this graph, so I assume this to be A and this is to be B. We have f of x, and all of the area under this rectangle has to be equal to 1. So as we know that the area of rectangle equals length, or the base multiplied by length. So we know that the base of this rectangle is b minus a, because this right here is b and this is a. So we say that b minus a gives you the width, gives you the base of this rectangle. So base into height is your f of x, and this should be equal to 1. So we can say that f of x equal to 1 divided by b minus a, which is your uniform continuous, or which is your uniform distribution function, or uniform distribution. So we just derive this formula for uniform distribution. Also, if you want to solve an example, let's say that this a is your this a is 2 and b is 4. As a is 2, b is 4, then what will be your f of x? So f of x equals 1 divided by 4 minus 2. It will give you f of x equals 1 by 2. So your f of x is equal to 1 by 2. Now, what if a person tells you to find the probability, or when x, assume little x, and that little x is equal to, we can say that when x is greater than, greater than 3. So for example, this is 3, and we have to find the probability of this area. We have to find the area under this graph, which is greater than 3. So what we are going to do is, you have the area this, so we will consider this as b, and this 3 we can consider. Now this 3 is going to be our a, because this is our smaller side. So we have um, p of x when x is greater than 3 equals, so we have to find the area. So we have 3, that is base, into height, that is 1 by 2. So 3 into 1 by 2, and that will give you 3 by 2. That is going to give you 3 by 2. So this is your probability when x assumes a value greater than 3. So yep, so this is the probability. For example, if a person tells you to calculate the probability when x is greater than 3 and less than 3.5. So what are you going to do now? So here, if here we use integration because you have two values here, so 3 and 3.5. So this, for example, let's say this is 3.5 and this should be your b. So we have so we use the integration. We have 3.5 and 3, and we have f of x dx. So how are you going to calculate this? What you're going to do is solve. So we have 3.5, 3, f of x is your f of x is 1 by 2 dx. So when you will calculate the so when you will integrate, you're actually going to get 3.5 minus 3 divided by 2, and this is going to give you 3.5 minus 3 equals 0.5 by 2. So 0.5 divided by 2, you can solve this. This is going to be your probability when p of capital X assumes little x, and that is greater than 3 or equal to 3 and less than or equal to 3.5. So also in statistics assignment, the teacher told us to solve two problems for your uniform continuous distribution. So here I solved one problem where the little x assumes a probability greater than, or you can also calculate this probability when little x assumes a value smaller than something like 3. So that'll give you a different answer. And here, yeah, and I also forgot to explain the right and left hand limits. So we already have covered our uniform distribution, and now we are going to go to our second topic, that is your left and right hand limits. Left and right hand limits, or you can say that you have one-sided limits. So for a function to have a limit, the limit exists if and only if you have right hand limit equal to your left hand limit. So if both of them are equal, then the limit of that specific function exists, otherwise it does not. So for example, if we have a graph um, like this, if we have if we have a graph like this, where there's a function where it's a function of where it's a function like this, and then we have a graph whose function is like this. So this is our 2, and this is our 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, and 4. So here, as we can see that here, let's say that, okay, so what is the limit of this function as x approaches minus 2? So we want to know that what is the limit of f of x of this function when x approaches minus 2 from the right side. So from the right side means from the right side, so from right hand to the left, so from the right side. So we put a positive sign on top of the number which x is approaching, so from the right side. So what is the limit of x when x is approaching -2 from the right side? It's actually it's actually 3, because it's approaching 3. At exactly at -2, its function is defined, but we were just want to we don't have to do uh, anything with the point where the function is defined. The limit is all about the approaching thing. So we have when x is approaching -2 from the right side, so it's actually approaching -3, so its limit is -3. But what if I ask you, what is the limit of this function f of x when x is approaching 2 from the left side, or from left side to the right side? That will be -2 minus, so this means that it is approaching from the left side, so that is also equal to -3. So that means, so -3 left hand right hand limit is equal to left hand limit, so that means its limit exists. But what about this? So here, what if I ask you, what is the limit of f of x when x approaches 2 from the left side, or from the left to the right, from the left side, yes, x approaches 2 from the left side, so 2 minus, that is if so from the left side, as we come here from the left, it is approaching 2, it is approaching 1. You see, it is approaching 1. But what if I ask you that what is the limit of f of x when x is approaching 2 from the right side? So from the right side, or from the right to the left, when x is approaching 2 from the right, so that will be positive. So when x is approaching 2 from the right, that is equal to, so from the right it is approaching 3.5, 2.1, 2.0001, that is approaching 3. It's equal to 3. As I've stated earlier, that when if and only if right hand limit equals your left hand limit, that specific limit exists. But here 1 is not equal to 3, so that means its limit does not exist. So that was the concept behind left and right hand limits. So the condition implies, if and only if your right hand limit is equal to your left hand limit, your limit exists, and if not, it does not. And now let's I also wanted to give you guys an idea about continuous and discontinuous function, continuous and discontinuous function. So here this is a continuous function because its limit and the continuous functions are the functions where at all the points on the graph your function is defined. So here at all the points this function is defined, but here this is also a function, this is also the graph of the function, but at 2 this point is not defined. At 2 exactly this point is not defined. So that is why we say that this function right here is a discontinuous function. It's not continuous. For discontinuous functions, limit does not exist. Limit does not exist for your discontinuous function. Whether on the other hand, for continuous functions, your limit exists. So also my throat is a little sore, so that's why I'm sorry if you guys have problem listening to me. But on the tour I had been on the tour for the whole previous week, and I didn't even sleep well there, and I shouted a lot, so that's why I'm having a sore throat. Never mind. So here, so this was the core concept behind left and right hand limits and your continuous and discontinuous function. I've also discussed uniform continuous distribution. Now let's discuss about the assignments, or the most awaited part. So we have assignment in programming fundamentals. In programming fundamentals, we are supposed to do one, two, three, a total of four questions from the programming exercise, and the most important and the most interesting one is the palindrome question, where you have to output where a user inputs a number and you create a function called is palindrome, and this function takes the parameter, and then it outputs the result, and on the screen it outputs that whether a number the user entered is a palindrome or not. And I did it in a different way, and my way is a long way. I usually, and I always like to do things I always like to do things differently. I know everybody would have done this the easiest way, but I did both ways. But I liked my own way better, so I did it on a different way, But you guys can do it on your own. It's pretty easy, but also a little tricky and challenging as well. You have two, three, and you have four questions in assignment, and in the stats subject, I've explained that you have two examples from uniform distribution. Alright, guys, this was it from me, and I'll see you guys tomorrow. Bye.